I do science at Wrocław University of Technology. I also wear a hat of consultant in mostly financial businesses. And I do a little bit of big data in telecommunications. And if you happen to go to Wrocław, please visit us. We didn't have a presentation for some time, but we are planning to have some new ones next year. So please come visit, maybe for a talk, maybe two talk. We are open. Also, as Google Summer of Code was mentioned, if you are looking for a mentor for the next year's Summer of Code, contact me. I did some mentoring in the ER project, so I can help you getting in the way in the process. So what I am going to talk about today. This is a case study, but this case study is made so that I can focus on some specific questions. And one thing I wanted to focus on is that if you have a full pipeline of analysis, which ends with some machine learning approach, whatever it is, whether it is the deep learning or something more classical or even simple linear regression, if this pipeline is deeper than just machine learning, you still should be able to introduce all those earlier steps into the pipeline so that everything is integrated and everything works together well. And another topic for my talk is that when you do preprocessing for the purposes of machine learning, it turns out that some of the intuitions you have from machine learning models also apply to preprocessing itself. And as it will turn out, there are some elements of preprocessing which you also need to have a dive into so that everything has a chance of working better. And as I said, it's a case study mostly. So what I do at the Wrocław University of Technology is that I studied glaucoma, and specifically I do analysis of biomedical signals related to glaucoma. Glaucoma, in Polish jaskra, is a disease mostly which mostly older people have, and it's a disease that leads to loss of vision. And vision is a pretty important thing for humans, so it would be nice if we could prevent stopping people see things. And as it turns out, glaucoma is a pretty difficult disease to work with because, well, firstly, it's very, very difficult to diagnose before some vision of loss happens. So if there's no vision loss yet, we don't really have any clues whether a person will develop glaucoma or not. Another problem with glaucoma is that we don't really have cures for glaucoma. We can only stop it going further. So there are some treatments that will help a person with glaucoma to keep the vision they still have, but you can't. Glaucoma is one of the elements of glaucoma is that some of the cells inside the eye die absolutely, so you can't regenerate them. And yeah, so what I exactly studied in my university work is something called Corneal pulse. So imagine that, every one of us has a blood pulse. Everyone here is probably still alive, yeah? So the heart is pumping blood, and this pumping is in a regular cycle. And it turns out that in response to that pumping of blood in our blood vessels, our eyes also pulsate. They slightly grow, then they slightly contract, grow, contract. And this is in response to the heart cycle too. This growing and contraction is on a very small scale. It's about 20 to 50 micrometers. So it's quite difficult to observe, but it's still here. And it not only follows the heartbeats, it also represents some biomechanical properties of the tissues around the eye. And this is important because one of the observed effects of glaucoma is that the tissues around the eyes become more stiff. And if something is more stiff, it's not flexible. It's not longer that flexible. So any pulsation is weakened or takes a different shape. And this shape is what we can observe in the corneal pulse signal. How do we measure it? This is the device. We actually do not touch the eye. So this is important because usually patients don't want their eyes to be touched, right? And we stick this device around 5 millimeters from the eye. And this device is actually a small camera which is based on ultrasounds. So it basically emits a wave. This wave returns back, and we register the distance by the time it took to get to the eye and back. So it's a very simple mechanism. And we can do this currently about 400 times per second. So this signal has a pretty high resolution. And if we have some ideal, maybe a bit simplified model of how this corneal pulse should look like, it should be a bit like this one. So we have a perfect response to the heartbeats and no other elements from stiffness of the eye tissue around. Our lab discovered at some point that there is actually some additional factor that mostly shows up in older patients. Older patients very often have a very small second peak in the signal in each cycle. And this second peak is called a dicrotic peak, like the second the second response to the heartbeat. It turns out that if someone has glaucoma, he usually has this second peak too. So we see some correlations between this dicrotic peak happening and glaucoma. So there's some venue that maybe this could be used for glaucoma diagnosis. So now the question is, firstly, how do we recognize whether a signal is this one or this one? And secondly, whether this thing is actually preluding to glaucoma or something else. I won't answer today to the second question, but I will talk about differentiating between the first and the second types of those signals. And it would be very, very nice if all signals were like that. They usually look like that. So you can probably see that there are some repeating features here, then here, then here, then here, then here, then here. They look roughly similar if you squint your eyes strong enough, but there are some other things here, like this thing. What do you think this is? Remember, this is eye, and this is a non-contact procedure. Exactly, someone blinked. Yeah. And there are other things here, slight movements of head. If you measure something on the scale of 20 micrometers, even very slight movement of a head will show up here as a huge response. So this is another example. This is probably breathing. When we do the measurements, we tie the patient's head to the device so that it doesn't move too much. Those are usually older patients, so we can't tie them too strongly because it hurts, actually. So, yeah, so we need to deal with at least some noise of this kind. So here are some assumptions, and I'll go over them one by one, but I'll note here that these assumptions show up in most of the signals coming from biomedical sources. So firstly, signal time series of scalars with equal spacing. We usually can assume that all those measurements are on equal spacing exactly, so we don't have any drift in measurement devices and so on. This is a very, very important assumption here because it helps a lot with methods. Signal is repetitive, not, I won't say cyclical, because this would invoke some stronger intuitions. There are some repeating parts, which we can usually visually identify as humans, right? So there is some pace at which those repetitions happen, and in our experiments, this is about 5% this or that way difference between the distances between repeated sequences. But well, Hertz cycle can jump from, let's say, 1 bit per second to 2 bits per second in almost an instant. So if you have some biomedical data from sports people, you will have a much more intense variation in repetitions. Okay. Internal variability, so noisy amplitude and compression or relations of parts. Sometimes things are longer, so sometimes things takes less time. So it varies also inside a repetition. Long-term trends, the thing I said, well, like head movements and so on. Outliers like blinking here. And even when we can split a signal into separate cycles, this doesn't mean we can do this perfectly. So our goal, we are on a machine learning conference, so one of the goals must be prediction and the second interpretability, right? Two goals, like usually. Data, we currently have signals from about 100 patients. Each patient has 2 eyes, and each eye was measured at least 3 times, so about 600 signals. And this is also an interesting thing. Glaucoma may develop in one eye, but not the other. So we may have differences between eyes of a single patient. Also, glaucoma diagnosis is not always very precise. There are some conditions that an ophthalmologist decide that this is a glaucoma or this is not a glaucoma. But like most of the human diseases, there are some corner cases, there are some, a doctor may decide that this is actually a glaucoma, despite that not all of the conditions happen. This is a bit messy. And even more messy is this dicrotism thing. We observe that this second peak happens often, but we don't really have a definition how it should look like. So we know it happens. We still don't have a precise definition for what dicrotism is. So we have some labels, but they are very noisy at this point. So when you have repetition in signals, the first thing that comes to mind to digital signal processing folks is Fourier transform. I hope I don't have to explain how it works. Do I have? Great, wonderful. So these are two Fourier transforms of two signals. One was dichrotic, the other is not dichrotic. How do you think which one is which? This is a frequency of 1 per second. This is 2 per second. So I also didn't know. So yeah. You can think that, oh, this peak and this peak look like they are roughly about at the places where they should be in a dichrotic signal. It turns out that the upper signal is a non-dichrotic one. So just by watching the Fourier spectra, it never worked well. And this is a method from, I think, late 70s. And we started thinking, okay, so let's drop the whole classical approach without any machine learning and start thinking about applying at least a bit of those slightly more modern methods. And we thought of a scenario like this. Let's try to average out all the signals, all the repetitions we have, and see how does the average repetition would look like. But to average just some random parts of the signal would never work because of those all shifts and different lengths of repetitions. For example, let's say we have 2 repetitions, each even of the same length, but they have the shift that makes a valley in one of the signals match a peak in the other. So they will average out to 0, but they are there. They will disappear, so it won't work. So we have to have some method to match the components of each repetition to each other, so that when we average out the signals, all those features will still be in the average. So let's say this is one signal, this is another signal, and the dynamic time warping method tries to pair up points from one to the other. So as example, pairing may look like that. The rule is simple. We start from pairing up the first 2 elements, and then we either move to another point in only one of this signals, or in both signals at the same time. But we don't skip points, and we may end up with a situation like this, where one point is matched to several points, because, well, sometimes parts of the signal that just disappear. So one more slide on splitting the repetitions. Here it's a simple thing. We measure, together with the Corneal pulse, we measure the electrocardiogram, and it turns out that it provides good enough way to split the signals into parts just by those peaks. Those peaks are called the R peaks from some nomenclature inside the field. So you can see that those peaks roughly match a specific part of the signal, one of the peaks. So when you apply dynamic time warping, you sometimes observe a diagram like this one, and I hope this is visible from the far ends of the room. Okay, so this is one signal, and this is another signal, and this curve tries to show which points from one signal match to which points from the other signal. And the dynamic time warping tries to make this curve such that the distance between specific points on one and the other of those signals are similar in some sense. You can actually define the distance manually. In this case, it was just an Euclidean distance. So it may look like not a big adjustment, here a bit and here something, some artifact, and the rest of the curve is almost straight on the diagonal, so no shifts at all. Does it look like a good or bad matching? Well, we see that this part of the one of the signals was matched to this part, or probably this part of this signal, right? And it used to be, here is a dashed line of the original signal, so it moved a bit here, right? So it looks like it works, right? Except there's a problem that this peak is not straight up and straight down. This is a hill that has some slope, specific slope, and it takes a bit of time to climb that slope, right? And after the time warping, we have vertical walls. This is not biologically plausible, right? So this a simple way of optimizing a procedure like that leads to certain effects that are not biologically plausible. And this is another example, which is even worse. Do you see that this signal has a valley, then a peak, a valley, peak, valley, and after the dynamic time warping procedure, it turns out that this whole part was squeezed into just few points. And this feature would probably absolutely disappear from the average later. Not biologically plausible at all. And when you see things disappear or totally getting out of control in machine learning, how do you call it? It's usually overfitting, right? You are optimizing something, some goal, which is not your actual goal, which is, let's say, to predict glaucoma here, but stating that you want to predict glaucoma is a very fuzzy goal. You need to state it in terms of mathematics, and so you need to make some proxy assumptions and some proxy goal, and you actually optimize that goal, and when this proxy goal does not match the actual goal, you get overfitting. So in this case, you have a preprocessing procedure that has actually the same problem as many methods in machine learning. Then we tried figuring out how to make it better. So let's say we are not actually using exactly the dynamic time warping approach, but just picking out some nice curves that maybe are closer to biologically plausible things. Here we chose the beta distributions CDF functions, which are nice because they always start at 0. They also always end at 1, 1, so we can easily use them for time warping because 0 is the start of the signal, 1 is the end of the signal, so we are always taking care of both ends. And they are nice, smooth, and what's more, there is a specific case, if you take alpha, beta equal to 1, you get a straight diagonal. So there is a function that represents no transformations at all. And it turns out that it works well in a similar way. Here I matched some signals, some example signals in points on those signals, so it's more visible. We moved this point here, and it matches this this peak. And again, the transformation does not look like a big one, but it works well enough to see those features on the average signal. And it turns out that when we applied this preprocessing method in our pipeline, which ends up with some machine learning later, it works just as well as the dynamic time warping, except with lower variance. Lower variance is usually a good thing. So again, relating to the machine learning ideas, I would call it inductive bias. Like, what is inductive bias in machine learning? It's the fact that when you have some algorithm, it usually has some solutions that are reached in an easier way, in a faster way, some preferred ones, and some solutions are are less preferred by a method. And here, despite that this curve is barely as flexible as the dynamic thermal warping curves, it works in the same way because the inductive bias is better. Okay, so then we tried a third approach. Let's just leave all those repetition splitting and so on. Let's try wavelets. Wavelets used to be popular at some point of time, and they are usually used when Fourier transform fails to work, at least by digital signal processing folks. So let's take this spiral, which is actually an exponential function in the complex domain. Let's multiply it pointwise by a Gaussian, and we get a function which is like a spiral that fades away from some distance. And it turns out that someone called it a Morlet wavelet. And when you have a shape like this, you can try to looking for a shape like this in our signal at each point of time and at each scales. So we actually take this function, scale it, stretch it, and compress it into different functions which represent longer time scales or shorter time scales. And we are looking for all those shapes in our signal. And when we do that, well, I am actually talking about continuous wavelet transform. This is different from discrete wavelet transform used sometimes in compression, so I'm making a distinction here. This is a heat map. The x-axis is following the time of the signal, and the y-axis is the scale. So the higher we go, the more stretched the wavelet is. And we are trying to figure out in which places we have this wavelet matching the signal. So this is one thing. The red one is very intense matching. The blue one is very low intense matching, so almost no matching. And we see that we have at some specific scales some matching, then at bigger scales no matching, and then at lower scales no matching. This is an example of a dichrotic signal of, I think, 4 repetitions. This is an example of non-dichrotic signal, so we see a clear difference, right? And here are some more examples on the left side, non-dichrotic signals and dichrotic signals. Do you see a difference visually? So now we need to plug it into some machine learning method to make it work instead of us just watching the signals and deciding, right? However, this is something we could actually show doctors, and they could decide on their own whether something is dichrotic or not, because humans are pretty good at detecting patterns, right? So then we plug it into some machine learning method. In our case, it was a very, very simple convolutional neural network. And we were computing also some parameters out of those images, like entropy and homogeneity, just to make some parameters that we can interpret. We plug it into, in this case, 3. And it turns out that it was, well, pretty fine approach. For 100 patients, we got something like 93% of accuracy, so it wasn't bad. And to make this work, we need to figure out some specific approach to do this image analysis. In our case, because we don't really have means to train a big network that would learn how to detect those shapes on its own, we decided that we will just do a very small convolution of 2 neighboring points, so very small, right? And then max pooling. Because, well, if we see that it's either that at some points we see high values and at some points we don't see high values, so maybe this max pooling is enough for that. some parameters we chose to have some control on this process, and this was selecting which specific points of those images we take into the analysis. So which rows of this image and how far the points would be to compare, like stride in convolutional approaches. And we were optimizing all those parameters from the preprocessing and from the machine learning approach together, because it turns out that we had several local minima in this optimization. For some settings of this preprocessing approach, we had trees that were quite fine for when they were deep, and for some parameters it was fine to have very shallow trees because deeper trees were overfitting. So again, joint hyperoptimization of hyperparameters was crucial here. We have a pipeline, and in theory we usually just optimize the hyperparameters of the final machine learning model. Here it was very, very interesting to optimize them both because they just work together very well. So this was the tree, and the time is going out. So yeah, this phrase I've read in a paper from 3 years ago, and I guess this explains a lot about machine learning, right? This phrase was actually used by some software engineering folks back in, let's say, 20 years ago, when they still didn't have the processes of building complex software worked out. And they thought that this is so complex that it just has to be this way. So, well, no, absolutely no rigorous procedures, and software that was very, very complex, that was several, maybe modular in design, but those modules were intertwined in very complex ways, so changing one thing affected everything else. And we have the same in machine learning, except we still don't know how to deal with that. So I like this phrase very much. It explains a lot about machine learning. And yeah, overfitting, inductive bias, some other terms which you probably can also apply into the preprocessing approaches for the machine learning purposes. So thank you for your attention. You can contact me on those email addresses. Thank you.